All right, our topic for the next 3 weeks will be plate tectonics and the Earth's interior. And so the way that we start this out is by discussing what is inside the Earth and how we know that. So let's just go right there. So first of all, um, the most obvious answer to how we know what's inside the Earth is we collect physical samples. And some examples here are listed. We can go out and collect chunks of rock from the crust. We can drill down into the crust, and we dig mines. So we dig holes in the ground that allow us to sample the materials that the Earth is made of as well. In addition to that, we can find out what the Earth and the solar system are made of by looking at meteorites, the moon, comets, asteroids, other planets. So all of those things give us information about what the Earth is made of. But that only goes so deep. In fact, if you go back and you look at some of these, about the deepest mine that we have is only about 2 miles. We've drilled, there are a couple drill holes in the continental crust that have gone down about 7 miles. We have never drilled or dug below the crust. We do have some samples of material that have come up from deeper. If you carefully sample igneous rocks, you can sometimes find materials that have been brought up from the next layer down, which is the Earth's mantle. So that's kind of the limit of our physical samples. So for the rest of our information, we have to have other sources. How do we look inside this large solid body that we call the Earth? The number one technique that we have, and these things listed on this slide are all part of a field of geology that we call geophysics. But our number one source of information is looking at seismic information, and we'll get into that in a little bit more detail on the next few slides. We can also use gravity, the Earth's gravitational field, large scale, like how we interact with other objects, and also smaller scale, like you can measure how strong the gravity is everywhere on the Earth's surface and look for variations in that gravity. And we can do the same thing with the Earth's magnetic field. We can measure variations in the Earth's magnetic field at the surface. So let's start with seismic information. First of all, the seismic waves that show up, there's a little seismogram in the upper right-hand corner. Your seismic station records seismic waves from earthquakes, really earthquakes around the planet. There's an extra credit exercise you can do on this that's linked from our schedule page that'll get you a little more detail on seismic waves. But your seismic station generally gets 3 sets of seismic waves. The P and the S waves are what we call body waves, and they come through the body of the Earth. And the body waves, there are 2 kinds of body waves. There are the P waves, which show up first. Those are the primary waves. You can see how they move through, the material gets compressed, and these are the fastest of the seismic waves, and that's why they show up first. The secondary waves are called S waves. The material shears, and the key thing to know about the S waves is that they do not travel through liquid. And so it's the body waves that we use to study the Earth's interior. The third set of waves that show up come in last because they travel around the surface of the Earth. It's shorter for the body waves to cut through the Earth. And so the surface waves show up last. And of course, because they're traveling on the Earth's surface, they don't really tell us much of anything about the Earth's interior. So what do we see? Well, the seismic waves radiate in all directions, and they will bounce off layers. They will be bent or refracted as they move from one type of material into another. And so we can develop a picture of the interior of the Earth. It looks something like this. And you can see on the right-hand side, this is actually a poster we have in the classroom. On the right-hand side, it shows you the different seismic returns or seismograms that you would get at different locations on the Earth's surface. And then the lines going through the planet show you the paths that the different seismic waves take. So what do we notice when we look at this? Well, there's a couple of things we're able to pick out. Number one, because of the way the seismic waves bend, we can identify the Earth's core. And also they will bounce off the boundary layer, and so we can use that to tell us something about the core as well. The other thing that happens is that S waves do not pass through the core. So you'll notice no S waves received here on the whole back side of the Earth, and that's because S waves do not pass through liquids. So that tells us right away that the Earth has a liquid core. A lot of the information you see on here is the kind of work seismologists have been doing for a very long time. With the advent of computer technology and the ability to process information at a very, very large scale, we've been able to do 3D, three-dimensional imaging of the Earth's interior, and that's a process that we call seismic tomography. So in addition to this kind of simple picture that we get of a core, and we'll actually see there's an inner core, but of an inner core, outer core, mantle, and then the very thin crust, we now have been developing three-dimensional pictures of exactly what's going on in the mantle, and that's what this is showing you. The other bits of information we have that I wanted to mention again are the Earth's magnetic field. This is a large-scale magnetic anomaly map of the Earth's surface. The anomalies that you see, the reds and the blues, show you strong positive or negative strength of the Earth's magnetic field, and geophysicists can use that to help interpret what's going on in the crust as well as the mantle and the core. This shows you gravity anomalies. Places where there's high gravity are red. Places where there's unusually low gravity is blue. And again, seismologists can use this to interpret the crust as well as what's happening in the mantle. So you don't need to know any more details about that, just that the gravity and magnetics allows us to see a little bit more detail about the Earth's interior. So they give us more information. So what are the layers? Well, we can look at the Earth's interior in two different ways. We can look at it compositionally, and if we look at it in terms of composition, we're going to have a core, a mantle, and a crust. But you can see on this picture there's actually an inner core and outer core, and so if we look at the state of the material, we see that the inner core is solid, the outer core is liquid, the lower mantle, and what's labeled on here, upper mantle, is what we call a ductile solid, which means it's capable of moving or flowing. And then the very outer surface of the Earth is the uppermost mantle plus the crust, and that is a rigid solid. And we're going to take a look at all of those in a little bit more detail. So let's start with the core. The composition of the core overall is predominantly iron and nickel, and this is based in part on a certain type of meteorite that we find, as well as information from the gravity, which tells us about the density, the overall density of the Earth. And the density of the core is estimated at around 10.5 grams per cubic centimeter. That compares to water, which has a density of about 1 gram per cubic centimeter. So it's about 10 times as dense as water. It's very dense material. The inner core is a rigid solid. So we're going to kind of leave it at that. It's solid iron and nickel. Kind of very interesting if we could get a piece of it, but we can't. The outer core, we want to talk about in a little more detail. Now, the picture I have here is lower mantle and outer core, but I want you to picture it actually, instead of lower mantle, think of this as the lower part of the outer core, because they both behave in the same way. Material at the boundary between the inner core, if this were the inner core, and the outer core, would be very hot, and that hot material is less dense, and therefore it rises up toward the top of the outer core, where it gives off its heat to the lower mantle, and because it gives off its heat, it becomes cooler. That makes it more dense, and it sinks back down. That process is called convection. So I use this image here because I like the way it looked, and I wanted to introduce the idea of convection. So picture the green part as being the outer core, and the yellow part being the inner core. And the same thing is going to happen at the core mantle boundary, where we're going to see convection as well. Now, this movement of an iron and nickel core results in the creation of what's called a geodynamo, and that's the source of the Earth's magnetic field. And if you'd like to learn a little bit more about that, I've added a link to a kind of a cool hour-long video lecture on exactly what's going on with the Earth's magnetic field. The next slide shows us the mantle, and I picked this picture because it shows you kind of a globby mantle. The red stuff is the material that is rising up to the top, to basically the crust mantle boundary, and the blue stuff is the cooler stuff that is sinking down. And we know this again from seismic tomography. So the mantle is a ductile solid. It is capable of flow, and that's kind of why I picked this picture, so you can see that. Its composition is ultramafic. You might remember when we looked at igneous rocks, one of those rocks was green. That is roughly the composition of the mantle. It's mostly iron and magnesium, with smaller amounts of silicon and oxygen. You'll notice that the density right here is about 5.5 grams per cubic centimeter on average, which is quite a bit less than the core, and that's why it sits above the core, because it's less dense. So let's move to the outermost layers, and these are the thinnest layers, but actually the ones we live on, so we're very interested in them. There are two ways to look at the surface of the Earth. We can look at it in terms of crust, and we can also look at it in terms of lithosphere. So let's start with the crust on the left-hand side. And you'll notice on the image in the upper right, you can see how this works. The continental crust is thick. It is felsic to intermediate in composition. So in terms of the igneous rocks we looked at, these are pink and gray. They're dominated by silicon, oxygen, sodium, potassium, and aluminum. And the overall density is about 2.6 to 2.8 grams per cubic centimeter. The ocean crust, you can see, is quite a bit thinner, only 3 to 5 miles thick compared to 10 to 25 miles for the continental crust. It is mafic in composition. This is the black igneous rock. It is dominated by iron and magnesium, as well as calcium, silicon, and oxygen. And you'll notice that composition is similar to the mantle, and this comes into play a little bit later. So that is not a coincidence. And you can see that it is a little bit more dense than the continental type crust. And last but not least is the lithosphere, the plates. When we talk about plate tectonics, the plates are lithosphere. And lithosphere is the crust plus a rigid part of the uppermost mantle. This is a rigid mechanical layer, and it's classified by the type of crust that you find on top. It floats on another part of the mantle called the asthenosphere. Again, it's a ductile solid. This is the uppermost mantle. It is very slushy. we think the top of the asthenosphere might